Assalamualaikum and hi everyone. In this video, we will be presenting about our scheduling problem, which titled Airline Crew Scheduling System. Before we go deeper into the details, let me introduce the group members. I am Huda Nasha binti Zrodin, then we have Nur Natasha Azila Nurisha, followed by Siti Nur Hamiza binti Hamza, Sofia Nadia binti Muhammad Zohri, and Nurul Alish Kalisha binti Hamni Elias Farid. Our intention is to optimize flight crew scheduling by balancing efficiency, safety and compliance with duty hours and rest periods. Crew scheduling is a complex NP-hard problem with multiple constraints such as flight schedule overlaps, crew qualifications, crew shift schedule and rest requirements. We aim to apply graph theory to model this problem using graph coloring techniques to ensure conflict-free scheduling. This approach will lead to more efficient scheduling and improve daily airline operations. Airlines face challenges in assigning crew to multiple flights with overlapping schedules, limited crew, and insufficient rest schedule. According to FAA 2018, this leads to issues like crew fatigue, flight delays, and increased operational costs.
Next, the objectives of this project are: we want to develop a conflict-free flight crew schedule by identifying flight overlaps and crew rest limitations using graph modeling. And we want to apply the graph coloring in Python to minimize the number of crew to be assigned. Overall, these objectives are aimed to optimize airline crew scheduling using a mathematical approach that improves both efficiency and operational safety. By using graph theory, the scheduling process becomes more systematic and easier to scale for real-world applications.
So, what are we solving and how do we solve it? In this project, we solve an airline crew scheduling problem using a graph theory. The aim is to assign flight crews to a set of 15 flight routes in a way that avoid overlapping flight duties, short or invisible crew transfer times, and violation of turnaround or rest requirement. Each flight is modeled as an edge in a network of airports. For example, F1 is a flight from Kota Kinabalu to Johor Bahru. The challenge is to assign minimum crew such that no two conflicting flights share the same crew. And how did we solve it? Our approach involved two levels of graph modeling, the flight route graph and the flight conflict graph.
First is the data collection. The data was collected from 10 major Malaysian airports using Google Maps to estimate straight line distance. A total of 15 flight routes were selected to form the scheduling network. Next is a flight route representation. Figure 1 shows the network of flight routes. Each airport is represented as a node with a specific color. Table 1 shows the mapping of nodes to their respective airport names and codes. This table presents the detailed flight schedule including departure and arrival times and flight duration for each route from F1 to F15. Next, we analyze the flight schedule to find conflicts like overlapping times or short turnaround. Each conflict was recorded as a connection between two conflicting flights. So this is conflict graph and matrix. Figure 2 is a visual representation of the conflicts, while Table 4 shows the adjacency matrix, which uses binary value to indicate whether the conflict exists between any two flights. We create a 50-50 matrix to represent the conflicts. A 1 means two flight conflicts, while 0 means. Based on the conflict and matrix graph, flights were assigned to 3 different crews. Figure 3 shows the colored graph representing crew assignments, and from the table, the result is clear that conflict-free assignments using only 3 crews.
For Objective 1, we aim to develop a conflict-free flight crew schedule by identifying flights overlaps and crew rest limitations using graph modeling. To achieve this, we examine 15 flight routes connecting 10 domestic airports in Malaysia. Based on flight departure times, durations and turnaround needs, we identify 13 conflicts, which include not enough turnaround, overlapping flight time, long shift durations, overlapping crew shifts, and also not enough time to relocate between airports. We model these conflicts as a graph where each node represents a flight and each edge represents a conflict between two flights. An adjacency metric was created to clearly visualize these relationships, ensuring that any flight pair in conflict would not be assigned to the same crew. For the second objective is to apply the graph coloring in Python to minimize the number of crew to be assigned. So the result showed that only 3 crews were needed. For the first crew is the crew A, which basically the blue one was assigned to flight F1, F5, F8, F11, F13 and also F15. While the crew B, which is the green one, was assigned to F3, F4, F6, F7, F9, F12 and also F14. And lastly, for the crew C, which is basically the yellow one, was assigned to only F2 and also F10.
In conclusion, this project has proven that graph theory, especially graph coloring, is a powerful tool for solving complex airline crew scheduling problems. By representing each flight as a node and each conflict as an edge, we were able to clearly identify overlapping schedules and prevent assigning the same crew to conflicting flights. Using Python and a greedy coloring algorithm, we managed to assign just 3 crews to cover 15 flights with no conflicts at all. This result shows that graph theory is not just theoretical, it's a practical and effective solution that airlines can use to plan safer and more efficient schedules. That's all from us. Thank you for listening, and we hope this project gave you a clear insight into how graph theory can help solve real-world scheduling problems.